actually build it. First, IF, instruction fetch. Later on, I expect you guys to be familiar with this acronyms, IF. Okay. This is where we fetch from the instruction RAM. We need to do a few important things. We do want to fetch the instruction. Right? So that's where we fetch this 2-byte long instruction into this register. So this is actually a multi-bit pipeline register. Okay. I'm not showing you how many bits, but we do have many bits. First, we need to use it to hold instruction. And we also want to place the current PC. In this case, we just do PC plus 2, and then we put it in the IFID. I'm going to explain later why we do PC plus 2 instead of PC, okay, into IFID. But we do need a PC. Okay, we do need to pass it into the next stage. It's going to be clear pretty soon. Then we update the PC. Okay, over here. We can either do the increment, either do PC plus 2, or this is the incomplete input. This is something that we are going to complete. This is where we have another input from the branch, right, the branching operation. And this one, PCJ, is the select for the mux, right, in front of PC. PCL is the write enable. L means load, write enable for PC. If PCL is 0, that's where we freeze. We do not load new instructions. We do not advance the PC. All right, so this is the first stage. Hopefully this is pretty straightforward. Right? Second stage, this is where we decode the instruction. We have something called ID, instruction decode. In this stage, we will need to push the 2-byte instruction through this decoder. Right? Again, just look at the color code here for these arrows, right? The black arrows. So these are the data. Okay, so this means the data, how data flow. The blue ones, like this, the ones coming out of the decoder, the blue ones, these are the control signals, right? Like the ones that drive the SB and SA, right? The source register addresses for RF. Okay, so in this ID stage, we read the source operands over here. We address RF, and then we read out data A here and data B here. We pass it to the next stage, ID/EX. We put it in this register. We also push in this one. Any guess what is this one? What is this one doing, this expression? IMM plus PC plus 2. Why do we save it here? Hopefully this also explains why we push PC, right, to this stage. Because we want to compute this one. We are using this adder. We are using this adder to do IMM. Sign send IM plus PC plus 2. PC plus 2 is from the previous stage. Next instruction, we actually want to push it to the next stage, right? This is still useful. This may be useful for the current instruction, may or may not. What kind of instruction may need something like this? Okay. If this is not clear, let's save this question. Oh, Lauren, yeah, good, very good. Branch, right? We'll see branch pretty soon. This is basically how we update the PC, right? When we take the branch. Again, this may or may not be useful. If we are indeed taking a branch, and the branch condition is indeed true, this is where this result is useful. Otherwise, we'll throw it away. Okay, we also do this. We also pass DR and LD into this intermediate pipeline stage, because we are not going to be writing the register file right away. We need to wait until the writeback stage. That's where we actually need to propagate it. We need to propagate its control signal through a few stages. Okay, any questions so far about ID? Are these lines clear? Once again, this is computing the PC, right? The updated PC address if you are taking a branch. And these are just the blue lines are just the control signals from the decoder. Next stage, EX, execution. This is where we actually perform the ALU operation. Right? This is the stage over here. In this stage, we do the ALU, right? And we also pass this guy. We pass this guy. See here, this is data B. Why are we passing data B? From this EX stage to the next stage? When we do this kind of passing, so we really want to make it useful, right? We want it to be used in some future stage, maybe in MEM, right? Very good, Katie. So this is where we pass data B for potential store instruction, right? Because we need to store data B in case we indeed have a store, right? If we have a store here in the MEM stage, it's a MEM stage, we are storing the value of data B, right? That's why we need to pass it along. Okay, is it clear? And we're doing the same thing here. We keep passing DR and LD to the next stage because we may need to use it later for writeback. This is the ALU stage. Let me try to ask another question. Is this ALU useful for branch? This ALU, is it useful for branching in this setup? Obviously, this is useful for doing add, right? Sub, right? Other things, shift, right? Those instructions. And it will be useful for doing store and load, right? For calculating the address. Is this ALU useful, potentially useful for branch? Yes or no? We already have some adder here, right? We already have the PC plus offset after this addition. So really my question is, why are we passing it here? Why don't we just write it back right away? Why don't we just update the PC in the second stage, in the ID stage? Why do we wait until the EX stage to update the PC? Let's just trace this line here. Right? Hopefully you guys see this highlighted line. Right? We wait until EX stage to do this PC update if we are taking a branch. This is where we have the second input for the mux, right? The PC mux. Very good. Okay, Emily and Steve, you're both right. We need, in this case, right, for this setup, we may need ALU to give us this Z and N, right? Whether this a zero or non-zero or overflow, right? So that we know whether we are taking the branch. In our instruction set, we only need this, right? Z and NZ, whether we have zero or non-zero. So we know whether we are taking the branch or not. But this actually brings up another question. If you take the branch in this stage, right, in the third stage now, right? IF is the first stage, ID is the second stage. This EX is the third stage. If you take the branch in this third stage, is it already too late? It's already too late. Then what is the potential problem? Okay, something to think about. Excellent point, Alma. So we are indeed using +2 for some reason, right? But is +2 enough? It may not be enough, right? Because we are taking it in the third stage. We actually need to do +4 somehow, right? Right, Emily, again, you are correct, right? So some of the instructions already in the pipeline, right? If we decide to take the branch, then somehow we need to figure out a way to throw away these instructions, right? We may be in trouble. This is something that we're going to discuss in the next lecture. But I want to make sure that you guys are aware of this potential, this so-called control hazard. This is a potential hazard in the pipeline. If we decide to take the branch too late, we may have to deal with the instructions that are already in the pipeline. Okay, because those will not be executed. Those cannot be executed, right? Okay. Any questions so far? EX? If not, let's move on to mem. In the memory stage, depending on whether we are doing certain operation or not, right, we will do different things. If we are doing a store, right, over here, we're doing a store, that's where there's a data big, right? The data big signal becomes useful because we are indeed writing to D in. Okay. Just want to remind you guys about the meaning of these control signals. When we are doing a store, if we are doing a store, what is MW? 0, 1, 1, very good. MD, you are doing a store. MD, what is MD? This guy, very good. We don't care, right? Because we are not writing back to the AOU. We're not writing back to the register file, not AOU. Okay, this is when we do store, we have X. Okay, right. This is also something that you guys need to be familiar with for Prim2, right? I may ask you guys about the control word. All right, so this is store. If you're doing a load, then we get the address, this address. Okay. For both load and store, we need address. This is what ALU gives us, right, from the previous stage, in the EX stage. In the address, we don't need this one. We pass the value that we fetch from the data RAM through this mux. Okay, so that's where we take we take this one. We take this pass. Okay. And for ALU operation, we just, so if we're doing ALU, you're doing ALU operation. Let's say we are actually doing add, R1, R2, something like this. What is MD? What is MD in the mem stage? This is the mem stage. This is 0, this is 1. Let's say this is 0, this is 1. 1, right? We take this pass. We want to bypass the data RAM. If we're not doing load or store, we take this pass. Okay. Once again, we pass DR and LD. We basically pass it all the way to the final stage. Okay. In the final stage, WB, write back. We write back. Okay. As simple as this. We follow this pass. We write it back to D in. If LD is 1, right? LD means whether we load or not for the register file. If LD is 1, we're going to use this backward pass and write the value back to D. Okay. So do we do write back do we actually write anything back for branches? Yes or no? Branches. Do we make use of this write back pass? Is it useful? Branching. Yes or no? No, right? It's not useful for branch. It's not useful for store. It's useful for ALU operations. It's useful for load. All right. So this is basically our pipeline processor. Okay. We have 5 stages, and we have these pipeline registers, right? Okay. We do need these registers because we will be executing multiple instructions at the same time, right? Just like our course pipeline. Right, so let's take a more abstract view of this processor. Again, we have 5 stages. Right? I'm hiding some of the details, right? The microarchitecture details. I'm gonna just use the boxes. This one indicates the instruction decode ID, but where we read the shading indicates that we are reading from the RF. Right? The shading on the right means that we are reading from the RF. This is the EX, this is a mem, the DM is data memory. Over here for write back, the shading here means that we are writing back to the RF. Okay. And let's say that we have 5 instructions in the instruction mem. This is IM is instruction mem. Okay. Let's see how the pipeline execute. Right? First, IF, right? We fetch the instruction. The first instruction is an add. This is the first cycle. Second cycle, we push add to the second stage, right? ID stage. We fetch the next instruction OR. Okay. Next cycle, add is in the third stage EX or second stage, and the new instruction sub. Sub is in the IF stage. So this arrow basically means the PC. Okay, we have 3-line here code, 3-line code here. We don't really have any branches. We are just using the arrow to indicate the PC. And we just keep going, right? And every clock cycle, we fetch a new instruction, and every clock cycle, we'll get to graduate an instruction, right? Retire an instruction, and etc. So this is a perfect pipeline, right? Where we have this so-called CPI near 1. CPI means cycles per instruction, right? We only need to spend near 1 cycle per instruction in the perfect pipeline. Okay, so this is the instruction sequence that I just showed you guys. This is another way to view this thing. Right? We start the IF, right, for OR in the second cycle. Okay, and sub starts in the third clock cycle, CC3. This is another way to look at the pipeline. I called it a Gantt chart. Later on, you guys will be using Gantt chart a lot, right? One thing that you can, when you write down pipeline, you can actually use additional shorthand, some other shorthands. You can just call it, for example, IF as F, right? Later on, I'm going to use this in my lecture as well. ID as D, let's use a single letter to indicate each stage. Instruction, the EX, not instruction, EX, execution as X, memory as M, write back as W. Then when we write down this Gantt chart, with the schedule, pipeline schedule, you can just write something like this. Okay, and third instruction, sub, okay, you can just do this. Right, instead of drawing the pretty picture like this. Okay? And each one of this is a cycle. And this kind of Gantt chart is going to be useful pretty soon. All right, let's look at different sequence. Pay attention to the things that are colored. If you guys already forgot about the instruction format, let me remind you, are we writing or reading our R1 here for add in this instruction? Is R1 a destination register or source register? It's a destination register, right? So we write to R1. In the second case, or we are reading from R1, right? Okay, so do we have a problem here or not? If there's a problem, what's the problem? Feel free to unmute and chime in. Okay, all right. Yeah, Katie just typed something up, right? Indeed, right, so we have a problem. We have a problem for OR because we are writing back R1 in cycle 5 for OR instruction with the current pipeline. Where do we read from the register file? Well, when do we read R1? In which cycle? Here, right? We have this backward dependency. We are building a pipeline, right? Not a time machine. We have a problem. right? We are reading something from the future. How about sub? Do we have a problem for sub for this R1? Can we get the correct value of R1 for sub? Yes or no? No. Same thing here. We are reading the register file, right? We are getting the value of R1. We're getting O value of R1, right? In cycle 4 over here. Okay, another backward dependency, which is bad. How about this guy? Is it good or bad? And do we have a problem? It's being read here, right? Do we have a problem or not? It is fine because it happens in C5. Okay, that's a reasonable answer, but the thing is there's actually still a problem. Why is that? We are writing to a register, right? How long does the new value of register shows up? When does the new register, when you write it at the current clock cycle, when does the new value shows up? Does it show up right away? No, right? It shows up at the next clock cycle. We talk about this, right? The register is like a delay element. It does not show up right away, which means that we also have a problem here. Is it clear? Okay. Now we have these dependencies which are not specified, which is bad. Okay, is it clear, guys? I'm gonna ask you guys to do a quiz, right? About this kind of data hazards. This is actually called data hazards because these OR, sub, and end instructions are data dependent, right, on the end instruction. But we are not getting the new value. We're not getting the updated R1. We are getting the OR1. The formal definitions here, we have something called hazard, okay, but it's called data hazard. Okay. You know, we also talk about hazard, right? In the glitches, right, in time analysis. This is a hazard for pipeline. When a register is read before the write back, then we have a so-called data hazard. I just show you 3 scenarios, right? 3 examples. What is supposed to happen is we want to get a new value of R1, right? We want to get the new value of this guy, but this guy will not be written back until this point, right? And we are reading from here, here, and here, which are too early. Okay. So coming back to the Gantt chart, right? I already talked about the Gantt chart, right? You know, for add. So one thing to look at this is, again, you guys can just write F, right? D, X, N, W, okay? F, D, X, and W. Let's just look at this instruction, these two, and OR. Okay. The important thing to identify data hazard is to first identify where do we update, right, the register. In this specific case, for our current pipeline, we're updating, we get the value here, right? Okay. And then you're just going to draw a line here. Okay. And we are getting we are reading it from here, right? And just draw this a line here. If it is backward, if it's not forward, then we have a problem. Okay. This is too late. Next lecture, we're going to talk about something more advanced. But first, let's talk about something more simple, something simpler, and something kind of dumb. Let's see how we can resolve this. We need to guarantee the correctness first, right? Before we talk about the performance optimization. Okay, so we really don't want this to happen, right? We don't want the third, right, the second, third, and fourth instruction to read the O value of R1. We need to somehow delay their execution. One way to delay their execution is by inserting these no ops. And you guys can just call it NOPS or no operation, but you know, we usually call it no op. We insert 3 no ops. So to delay the OR instruction. So all here, I'm assuming that the compiler is smart enough the compiler will actually try to analyze the dependency between this instruction. It is done by construction. SW means software. The compiler will insert this additional instruction, no-op instructions, in the instruction sequence to guarantee correctness. So we are inserting 3 no-ops here, right? So that we have a forward dependency. This is where the data hazard is resolved. But there's an overhead, right? Because we are no longer executing a useful instruction in certain cases. Like these are not useful instructions. That's where our CPI, right? The cycles per instruction will increase, which means we have a performance overhead, which means that we don't have an ideal, a perfect pipeline. Okay, any questions about this? Again, just a heads up, right? So there will be a quiz at the end. So if this is not clear, why are we inserting no-op? And why are we inserting 3 no-ops here? Make sure you ask now. Okay. Looks like this makes sense. The other way that we can handle this is by relying on some smart hardware. We can also try to detect this kind of dependency on the fly. We're going to be talking about this in maybe in the week after, right? We're going to talk about how we detect these kind of dependencies on the fly in the actual microprocessor. So the microprocessor can also insert sort of hardware no-op. We could just call it a bubble, can delay an instructions on the fly. So this is where we fetch the second instruction, and if we detect after the decoding, we detect, oh, there's actually dependency. Then let's just delay this the next stage. Okay, let's don't do it right away. Let's delay it also by 3 clock cycles. In terms of the performance, this is pretty much the same, right? We also delayed the instruction sequence by 3 clock cycles. But in this case, we are assuming that the hardware, HW means hardware. Hardware is doing the hard work. In the previous case, in solution 1, we are assuming that the software, the system compilation, right? The system compiler is doing the hard work. The hardware is done, right? In the previous case, in this case, the hardware is more intelligent because there's more hardware overhead. Okay, again, we delayed it for 3 clock cycles in the current setup. That's how we can avoid the data hazard. All right, and then we have this forward dependency. If this is still not so clear, right before the quiz, so let's go through one more exercise. Okay, here's the instruction sequence. Let me ID these instructions. Okay. So the question is, do we have data hazards between some instructions? If so, circle the register, the source register. We do have a no-op here. We do have one no-op here. Okay. All right. So first question, do we have data hazard for this instruction? For add 1, yes or no? If yes, on which register? Circle the register. Very good, yes, R1, right? We do have a dependency here because one no-op is not sufficient. We actually need 3 things, right? We need 3 instructions in between. Otherwise, we have a data hazard, right? Because we have writeback. Writeback is in stage 5, but ID, right? We decode the instruction and read from register file in ID stage. That's in stage 2. We need 3 instructions. We need 3 no-ops or other instruction to separate these 2. Otherwise, we do have a data hazard. Okay, so that's that. Do we have a data hazard for instruction 4, the sub? Yes or no? If yes, which instruction? Also R1, right? Again, we only have 2 instructions in between add and sub, right? Between this guy and this guy. It's not enough, so we also have data hazard. Okay, last question. Instruction 5, or do we have a data hazard on R1? Not on R1, right? but we do have a data hazard on R3 because R3 is being written by sub in the previous instruction. Okay. Any questions before we do the quiz? All right. Looks like this is clear.